time we talked about ionic bonding, metallic bonding. We got into covalent bonding, and we started digging into Lewis structures. So Lewis structures is the topic for today. Now, before I get into Lewis structures, I do want to kind of discuss electronegativity. Now, you don't have to have Lewis structures to figure out electronegativity because it is a topic that is a periodic trend. So that's where I'm going to actually pick up right now here. So what is electronegativity? Excuse me. All right. So electronegativity, I'm going to type this out here for you guys. So the ability of an atom in a molecule to attract shared electrons to itself. That's the definition of electronegativity. Now, the scientist that is given credit for this is Linus Pauling. For his method and determining the values of electronegativity. So you do not have to worry about the values at all. What you have to do is basically have an understanding of electronegativities. Now, so I'm going to kind of give you a general idea of how the trend is on the periodic table here. So we know that there are noble gases over here, but we don't worry about them. So when I'm not going to even talk about them. What I am going to talk about is fluorine versus cesium. And so remember that fluorine, if we compare the sizes, fluorine is a tiny atom as compared to cesium, which is a very large atom in comparison to. Now that goes back to ionization energy as well. So we talked about ionization energy the last time, and we said that the fluorine, since it's in the upper right hand corner, is going to have a higher ionization energy than cesium because it's smaller in size. So fluorine has a higher ionization energy. Now, the same thing holds true with the fact that we talked about valence electrons. Okay, so this ties in. So there are 7 valence electrons for fluorine, and there's 1 valence electron for cesium. Now, what does electronegativity deal with in reference to these? Now, keep in mind that nonmetals tend to want to attract more shared electrons to it. And so that goes back to size, ionization energy, all that ties together here. So fluorine is going to have a higher electronegativity value than cesium. In fact, on the periodic table, the trend goes in this direction. The trend increases in electronegativity from bottom to top and left to right. So fluorine is going to have the high electronegativity value on the periodic table in comparison to cesium. Now, in your book, there's actually a table that lists the numerical value for electronegativities, okay? So you'll want to at least find that table, and I'm trying to find it for you here so it's easy for you to find. Let's see here. So this is going to be, I think, in chapter 10 here, towards the beginning. All right, so page 407, so page 407, you have the chart that gives you all the electronegativity values. So fluorine's electronegativity value is 4.0. It's the highest on the periodic table. And then cesium is 0.7. And that goes back to the size. That has a lot to do with it. So looking at just a couple other elements, so hydrogen. Hydrogen is a very small element. It's up to the top. So hydrogen would be found right here. So it's higher up. So hydrogen is going to have a higher electronegativity and value, and specifically it's 2.1. Now lithium's right below it. Lithium, I'm getting all these values from the book, by the way, it's 1.0. So there's a big difference between hydrogen and lithium. But keep in mind that hydrogen is an oddball. Hydrogen can act as either a metal or non-metal, and so that's why it actually fits best in between boron and carbon on the periodic table. So boron has a value of 2.0, and then carbon has a value of 2.5. So hydrogen's a weirdo, like I said. Hydrogen fits in the middle there. So, but when we talk about these values and we try to figure out the, what's the point of knowing the values and how can we use them? So what we can do is we can figure out the delta En. What we can do is you just figure out the difference between the two elements. So let's say we have HF, and now so HF, so hydrogen's 2.1, and then fluorine is 4.0. All right, so the difference between those two is going to be 4 minus 2.1, which gives me 1.9. Now, you have to ask the question, so what exactly does that mean? What's that important for? Why do we need to know the change in electronegativity value? So keep in mind that what I'm about to tell you is something that I learned, and it's something that I use. Now, if you look at a textbook, they might give you a different set of values, ranges, etc. So what I'm going to tell you here is what these differences in electronegativities represent. Now, this is what helps you to predict the type of bond. So there's different types. So there's non-polar, covalent. There's polar, covalent. And then there is the last one, which is ionic. Now, the change in electronegativity value range that these happen to be in is 0 to 0.3. Keep in mind that these are not fixed numbers. They really depend on the compound, but it gives you a general idea as to what they might be as far as the type of bond. It's not telling you the type of compound. It's talking about the bond specifically that holds the hydrogen and the fluorine together. All right. Now, the polar covalent ranges between 0.3 and 1.7, and an ionic is 1.7 to 4.0. Right, so it has a pretty broad range. Now, so HF is an oddball because HF is actually considered to be a weak electrolyte, so it does dissociate, but very little amount of it dissociates, and so that puts it right around, if you look at the value, it's 1.9. So it's right along that threshold of changing from polar covalent to ionic. Now, in our case, we would consider to be more of a polar covalent compound because when we draw its Lewis structure, we actually physically draw a covalent bond in between the hydrogen and the fluorine. Now, the fact is that it's an oddball, and it fits really in between polar covalent and ionic. Now, right now, we're just kind of trying to make some sense of that. But when you get into chemistry 152 in the spring, assuming that you take it, you will see what we're talking about a little more specifically. So that's why I say you have to take this table, these ranges, with a grain of salt. And so you got to use your best judgment for it. Now, keep in mind that the polar bond doesn't necessarily mean it's a polar molecule, and that really ties back into the Lewis structure and how it's drawn. So if we look at H2O, all right, so H2O has a hydrogen and an oxygen bond. So we look up the electronegativity values. Now hydrogen is 2.1, where oxygen is 3.5. So 3.5 minus 2.1 gives you what, around 1.7. 1.3 or something like that. Yeah. Brain fart there. I don't know what the heck's wrong with me. Can't even do simple subtraction. I don't know why that happened. 1.4. Now that clearly fits in polar covalent. So that's the type of bond that oxygen possesses. So now I'm going to go back to the other day where we talked about the molecule. So we drew the Lewis structure for water, and we had a Lewis structure that looks like this. Remember, the lone pairs go around the two pairs of electrons on the oxygen. So with this bond here between the oxygen and the hydrogen, the oxygen is more electronegative than the hydrogen, and this is really where this comes into play. So there's a pull going towards the oxygen. So let me just explain to you what this little arrow means. So the arrow means that it's pulling towards the oxygen. So this is the more electronegative element here. And then, so when it pulls the electrons towards the oxygen, it creates a partial positive charge at the bottom. And that's why we draw this sort of this plus sign on the hydrogen, because as it pulls electrons away, it causes hydrogen to be partially positive. Now it's not a full positive charge. The symbol we use for that is like a 3/4 8. So we have partial positive, and then we also have partial negative. So the oxygen is partial negative because it's more electronegative than the hydrogen, which makes the hydrogen a partial positive. So these arrows that we draw are actually called dipole moments. All right, and so dipole moments are formed in between two elements that have a difference in electronegativity value. So if we go back and we look at HF that we just looked at, all right, we saw that HF has a difference of, what is it? Where did HF go? Of 1.9. So the hydrogen is 2.1, the fluorine is 4.0. So you're going to have a dipole that pulls towards the fluorine. So what's that doing? That creates a partial positive on the hydrogen and a partial negative on the fluorine. Now these dipoles that are forming here are permanent dipoles. Now there are compounds that form dipoles, but they cancel themselves out. And so that's what I'm going to look at next. Is give you an example. So let's look at CH first. Okay. So carbon again is 2.5, and hydrogen is 2.1. So that's going to give you 0.4. So that fits right into the polar covalent section type. So that gives you a polar covalent bond. So when we look at the compound CH4, all right, so carbon has 4 valence electrons. Hydrogen has 1, so you're going to put a hydrogen. I'm going to just go ahead and draw a bond in between the hydrogens and the carbon here. Okay, so we have 4 single bonds to the hydrogen and carbon. And so when we look at just one single carbon-hydrogen bond, what we see here is the carbon is a little bit more electronegative than the hydrogen. So you're going to have a dipole that's pulling towards the carbon. Now, each of the hydrogens is going to pull towards a carbon. So they're pulling towards a carbon. And as a result, so there's nothing that's going to pull in the opposite direction. So they have nothing to really create any problems or disorganization, I guess you'd say. So what happens is the dipoles cancel out. So these dipoles will cancel and cause CH4 to be non-polar. So that's where you got to be careful, is the fact that, hey, look, the bond is polar, but the molecule itself is not polar. So you have to be really careful in how you go about solving for that. Are there any questions with that?
Nope.
So you can do this for a lot of different compounds. Now, how often are we going to use electronegativity values? Not often, because you'll have your periodic table. And on the periodic table, you can actually distinguish the more electronegative elements because it increases up and to the right. So we know just by nature of the periodic table that the fluorine, the upper right hand corner, is going to have the highest electronegativity values, whereas the ones on the bottom left are going to have the lowest. So that's just a pattern that you're going to have to make sure you retain and not forget. So now, as we start to talk about polarity, we continue that discussion. You know, polarity, you know, we talk about types of bonds. Well, okay, that's fine. Ionic is simple. It's metal to non-metal. But when we start to look at the differences between polar and non-polar, now we start to have to look at specifically the compounds themselves. So if we look at, two different compounds, we look at I2, and then we're going to look at, let's see, I don't want to do too much here. IBR, that'll be a good one to do. All right, so now I2, so the first thing you do when you draw the Lewis is you got to figure out how many valence electron each atom possesses. Now, so iodine has 7. There are 2 iodines, so that's a total of 14 valence electrons. Okay, so let's just draw out the iodines and their dot structure. So you have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So the magic number here again is an octet, so 8 valence electrons. So the atoms do not want to exceed the octet rule. All right. So when you look at this, you've got 7 on the one on the left, and you have 7 on the right. So basically, what we're going to do is just going to draw a single bond in between the 2 iodines. Now that single bond, remember that for every bond you have 2 electrons. So now you have 2, 4, 6, 8 for the left, 2, 4, 6, 8 on the right. So everything meets the octet, so we're good to go. So we don't have to worry about anything there. So that molecule is now done. Now let's look at the IBR. So again, iodine is 7. Bromine is in the same group, so that's 7. It's a total of 14. Now you're saying, well, why do we need to keep track of how many electrons? Okay, to make sure you don't put too many or not have enough. So I'm going to go back to I2 right fast just so we can see that and clarify that. So I'm just going to highlight the pairs. So 1, 2, 3, 4, 5, 6, 7. Now there are 7 pairs. 7 times 2 gives me 14 electrons. So that lets me know that I have the right number of electrons. All right, that's why we do that. Now, these smaller compounds, they are not a problem because they're easy to count. When we get to compounds that have 32 and 48 electrons, then we really got to be careful and make sure that we have the right number of valence electrons. Okay, so let's look at iodine. So you got 1, 2, 5, 6, 7, and then bromine 1, 2, 3, 4, 5, 6, 7. and I'm going to draw a bond. So it's identical to what we just saw there. All right, so the same setup, same format. They all have 8 electrons, so therefore they're valid for the octet rule. Now, here's the difference though, okay? So iodine has an electronegativity value of 2.5, and bromine is 2.8. So 2.8 minus 2.5 gives me 0.3. So you're right on that boundary line here, okay? So up here for the I2, or this is 2.5, this is 2.5, so the difference here is 0. So the change electronegativity is 0. So this one's easy, okay? So this one's nonpolar. That one's very simple to figure out. Now, as we look at the IBR, so iodine is less electronegative, so you're going to have a pull towards the bromine. Now, so you're right on that threshold. Remember, the threshold is like 0.3. It could be polar or it could be nonpolar. Now, this case here, you have a dipole pulling towards the bromine, so that causes the bromine to be partial negative and iodine to be partial positive. So that means that IBR is a polar compound. So that's where you really got to be careful. And you can use your textbook's table to help figure this out, but keep in mind that sometimes you're on that threshold. You really have to be able to distinguish using the Lewis structure. In this case, the Lewis structure makes the difference. All right. So let's look at another one here. So let's look at NH3. All right. So NH3. So nitrogen has 5. The hydrogen has 1, and there's 3 of those. That's a total of 8 valence electrons. So nitrogen goes in the middle. All right, 1, 2, 3, 4, 5. All right, I'm going to go ahead and put a lone pair on it because we don't want to bond on a pair. The pairs are staying as pairs. And then you have the hydrogens. So you're going to put a hydrogen along each of the single sides. So then you'll have your bond here. So you have these single bonds. Now, if we just look at nitrogen to a single bond hydrogen, so nitrogen is 3.0 and hydrogen is 2.1. So that's going to be a difference of 0.9. So subtract out, give you a difference of 0.9. So that represents a polar bond. All right, so it's a polar covalent bond. Now let's look at the compound and let's see whether that holds true. Okay, so again, the nitrogen is more electronegative, so they're going to have a dipoles pulling towards the nitrogen. Now, we have the one on the left and right, looks like they cancel out, but let's look at the bottom here. So the bottom is pulling towards the nitrogen. There's nothing pulling back against it, so guess what? That makes this compound polar. And so your net dipole is pulling towards the nitrogen in this example. So this is a polar compound. And it still has a polar bond. So this is where the bond in the compound does match up nice and neatly. So, but that's the way you go about figuring it out. You have to draw the Lewis structure, and then you look at the electronegativities, and you draw your arrows pointing towards the more electronegative, figuring out if one cancels out with the other. If they all cancel out, it's nonpolar. If they don't all cancel, then you've got your answer. It's very easy. So let's do one together. Let's do HCl versus Cl2. I want you to draw the Lewis structure for these two, and I also want you to figure out which one is polar and which one is nonpolar. All right, so Lewis structure and polarity. All right, so I'm going to give you guys 2 minutes here. Actually, I'll give you till 10:30. It's 10:27. So at 10:30, I will come back and we will go over this. So try to have an answer, please. You've got a minute left. All right, so HCl versus Cl2. All right, we're going to look at this. So HCl, hydrogen has 1, Cl has 7, 1, 2, 3, 4, 5, 6, 7. So you have a single bond to the chlorine here. Now looking at CO2, you should have a single bond in between the two Cls that you see here. So there is a pull towards the chlorine because chlorine is more electronegative. And now in the case of the Cl2, they're both the same, so there's no dipole there. Now that automatically suggests that this one is nonpolar. And since HCl has this dipole, that means that it is polar. And that's how you determine the answer here. So HCl is polar, whereas Cl2 is nonpolar. Any questions on that? All right. So on Moodle, I have a document. I showed you guys this last week, and let's see if I'm logged in still. Nope. Log in right fast here. On Moodle, there's a document that I've posted. It's been on there the whole semester, but I just want to point it out to you here. So if you scroll down to the section that we're in right now, you'll find so they've got the videos here, Vesper sheets here, and okay, here it is. So drawing Lewis structures for charged molecules. I want you to go through this document here. I want you to keep a track of everything that I do, because this is talking about how you draw Lewis structures for charged compounds. And so I want to move on from the Lewis structures and the molecular geometry and hybridization on Wednesday, and then we're going to do molecular orbital theory on Friday. And you'll have your, well, we might actually do that on Monday, depends on where we get to, but your exam will be when you come back after the break. So please watch this. Now, as we talk about, continue this conversation with Lewis structures, we're going to get into a new section here, and that new section are exceptions to the octet. So exceptions to the octet rule. So there are elements that can exceed the octet and have up to a maximum of 12 valence electrons around its core. These elements are located in periods, let's see, 2 and higher on the periodic table. So elements carbon, nitrogen, oxygen, and fluorine are to never exceed the octet rule. And that's a very important detail to write down and remember. So CNOF is what I call this, and that sounds weird, but CNOF is the way you remember. Now, the reason why those elements are like that is because they're the foremost electronegative elements. So those 4 elements will always have 4 valence electrons. All right, a bonding of 4 pairs, I should say. So CH4 was a good example. NH3 was a good example. H2O was a good example, and then HF. So we've looked at 4 different examples that contain this rule where these will not exceed the octet rule. Now, as we move on into the exceptions to the octet rule, there are a few that we have to look at. And you don't always have to exceed the octet rule. In fact, some elements don't exceed the octet rule. A good example would be, let's say, BF3. All right, so BF3, we're looking at boron here specifically. All right, boron has 3 valence electrons, and then you have the 7 times 3 here. That's a total of 24 valence electrons in that compound. But boron is the one that we're really focused on here. So boron is your central atom, and it has 3 dots around it. Okay, so now how many electrons can exist in a bond? Only 2. So if we draw a bond here, and it doesn't matter what other elements on the other side, boron's going to have 3 bonds. 3 times 2 equals 6 valence electrons. So the most electrons that boron can have are 6. So boron actually does not exceed it. It's below the octet rule. So to finish this Lewis structure out, you'd have the fluorine that has 7 around it, and so you're going to have a single bond to the fluorine. But you also notice that the fluorine is going to have valence electrons, 8 of them specifically. So you have 8, 8, and 8. So those fluorines achieve the octet, which they have to. And then boron doesn't achieve the octet because it can never exceed. It can never have 8. The most it'll ever have is 6 valence electrons. Any questions on that?
No.
At least I know one person is with us. I don't hear anybody else. Where's everyone at? See what I mean? I guess, are they writing in the comments? Sydney?
I'm here. I just have a child.
Yeah, okay. All right, so let's look at another one here. All right, so let's look at PCl5. PCl5, so you have phosphorus has 5 valence electrons plus the chlorine, which is 7 times 5, total of 40 valence electrons. This is where you have to count. We didn't count previously in the boron and the 3 fluorines, but I know that they're correct because of the way the electrons are arranged. You might want to count the PCl5 after we're done. So phosphorus has 1, 2, 3, 4, 5. It has 5 valence electrons. You might be on, this might be the part that confuses you because you'd want to draw an earlobe around the lone pair, which you should not do that because, so phosphorus has 5 valence electrons, and I'm going to draw this a little bit differently because we have to make room for 5 chlorines. Now, you're going to see something like this show up. You'll never see the 2 chlorines bond together like that. That's not going to happen, okay? What you'll see is you'll see the chlorines bonding around the phosphorus utilizing the 5 free valence electrons that the phosphorus has here. So you end up having a Lewis structure like this. And yes, you have to draw all the dots around each of the elements. You have to keep up with that. Now, I can go around and I can see that the chlorines at 2, 4, 6, 8, 2, 4, 6, 8. So every chlorine achieves the octet rule, and they should on the outside. It's the central atom that can exceed the octet rule because it has to. There's no other option for it because it's got to bond with all 5, and that's how it's going to do it. It's going to share all of its electrons. Now, and so in this case here, you have 2, 4, 6, 8, 10. So phosphorus has 10 valence electrons. And that's okay because phosphorus can have 8 or 10 valence electrons. Let me rewrite this. So 8 or 10 valence electrons. So phosphorus is okay with that. All right. So let me give you guys one to do, okay? All right, so the best thing to do is practice. All right, practice makes perfect here. So I'm going to give you guys one to do, 2 minutes to do it, CLF3. All right, so this is CLF3. All right, so 2 minutes, starting now. So 10:43, I'll come back. All right, get started, please. Draw the Lewis structure. If you want to figure out the polarity, do that as well. Get time to do that and practice it. So you should be getting close to being done with this one. And in fact, let's get started with it. It's 10:43 now. So all the elements have 7 valence electrons. So 7 times 4 gives me 28 valence electrons total. So chlorine is going to be your central atom here. Now keep in mind that fluorine F has to follow the 8th rule, the octet rule. So you've got 1, 2, 3, 4, 5, 6, 7. What you're going to do here is now the first fluorine's easy. So the first fluorine is going to be bonded right here. That one's easy, not a problem. It's the second and third fluorine that's going to be challenging. It's not a challenge because what we're going to do is they've got to bond somewhere. So we're just going to put them here and here on these 2 valence electrons for chlorine. And then we're going to draw our 7 around the fluorine to make sure we have the right number. So this has 8, 8, and 8, so that's good. Now, the chlorine also has 2 lone pairs that are left. So we're just going to go ahead and put here left. We're not going to do anything with them, just representing that they're lone pairs. So now we have our Lewis structure drawn. So we're going to count this one just to make sure we have 28. All right, so I'm going to use highlighter. I'm going to highlight them. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28. So we have the right number of electrons. So that's a good thing. Is if we didn't have the right number of electrons, we need to go back and figure out what are we missing, what did we do wrong. It's a way of checking yourself. Okay. Now this molecule, just kind of cleaning this up a little bit, looks like this here. So you're going to have sort of like a triangle here. So the element that's more electronegative is the fluorine. So it's going to have a dipole pulling towards the fluorine. This is not going to cancel out, so this compound is going to be polar. All right, so that's a polar compound. Now, if we go back and look at the other one that we just did, PCl5. So you look at the PCl5. Yeah, the chlorine is the chlorine more electronegative than the phosphorus? Let's see here. No, it's the chlorine's more electronegative. So I'm gonna draw this in red just so we can see it a little better. So we have a pull this way, this way, this way, this way, and the opposite way. So clearly there's pulling in all the directions, and so they're going to cancel each other out. So therefore this compound is going to be non-polar as a result. So we're looking at polarity here. We looked at Lewis structures. We talked about Lewis structures that exceed the octet rule. All right. So homework. You're going to have some homework to do here. Okay. So I want you to draw. So draw Lewis structures and determine polarity. All right, so I'm going to give you guys 5 compounds to do here. All right, so the first one is going to be XeO3. The second one will be BeCl2. And let's see, I told you 5. So third one is going to be CO2. The fourth one is going to be CO. And the fifth one is going to be NO with a +1 charge. Okay, so you're going to have to go back and look at that handout that I showed you on Moodle. So you're going to have to go back and look at it. All right, so this is your homework. All right, so you guys will be responsible for answering all 5 of these. I'll post an assignment tab on Moodle under the Lewis structures, so you can upload your answers and show all your work. And I want you guys to have that done by the end of today. So I'll have that live here in a short bit. All right.